Imagine a world powered by the very light that bathes our planet. Solar energy holds immense promise for a sustainable future. At the heart of this revolution lie materials called perovskites. These remarkable crystals possess a unique ability to convert sunlight into electricity with incredible efficiency. Scientists are constantly exploring the hidden potential of perovskites, unlocking the secrets to even greater performance. One such secret lies in the fascinating world of ferroelasticity, where crystals can bend and deform under the influence of external forces. Perovskites, named after Russian mineralogist L.A. Perovsky, belong to a class of materials with a specific crystal structure. This structure gives them their remarkable properties, including their response to electric fields. Understanding the behavior of these crystals under electric fields is key to optimizing their use in solar cells and other electronic devices. Our work mostly focuses on ferroelasticity's behavior on solar cells' performances. Crystals are often imagined as rigid, unyielding structures. However, some materials, like certain perovskites, exhibit a fascinating property called ferroelasticity. Imagine a flexible ruler. You can bend it with a little force and it will return to its original shape when you release it. Ferroelastic crystals behave similarly. They can undergo reversible shape changes or deformations under mechanical stress, much like our ruler. This flexibility stems from the arrangement of atoms within their crystal lattice. These deformations aren't random. They occur along specific crystallographic planes dictated by the symmetry of the material. Think of it like folding a piece of paper. You can fold it along specific lines, but not just anywhere. This ability to deform reversibly makes ferroelastic materials incredibly interesting for various applications. It's like having a building that can withstand earthquakes by slightly shifting its structure. Within the crystal structure of ferroelastic perovskites, a fascinating phenomenon occurs: the formation of twin domains. Imagine looking into a mirror and seeing a reversed image of yourself. Twin domains are similar. They are regions within the crystal that are mirror images of each other. However, these mirror images aren't just visual. They have distinct crystallographic orientations, meaning their atoms are arranged differently. These differences in orientation have significant implications for the material's properties. While chemically identical, twin domains can exhibit different electrical and optical characteristics. Imagine two identical twins with completely opposite personalities. Similarly, twin domains, despite their structural similarities, can behave very differently. This difference in behavior arises from the varying alignment of electrical dipoles within each domain. It is interesting and important to know how an electric field can influence the ferroelastic twin domains of perovskite. In addition, how is internal stress produced under an external electric field? An electric field acts as a guiding force, influencing the arrangement of these twin domains. Think of it like using a magnet to organize iron filings on a piece of paper. The electric field encourages domains with favorable orientations to align. This process, known as electric poling, allows us to manipulate the internal structure of the perovskite twin domains. By controlling the strength and direction of the electric field, we can essentially tune the material's electrical properties. It's like having a remote control for the crystal's internal structure. This ability to manipulate domain structure through electric fields opens up exciting possibilities for optimizing perovskite materials for specific applications. Electrostriction, squeezing and stretching the crystal lattice. The application of an electric field doesn't simply rearrange the twin domains, it also directly affects the crystal lattice itself through a phenomenon called electrostriction. Imagine squeezing a stress ball. The pressure from your hand deforms the ball. Similarly, an electric field can squeeze or stretch the crystal lattice, altering the spacing between atoms. This squeezing and stretching, while subtle, have profound implications for the material's properties. Remember how the arrangement of atoms dictates the material's behavior. Electrostriction allows us to fine-tune these atomic distances, further influencing the crystal's electrical and optical characteristics. It's like giving the crystal a gentle massage, subtly rearranging its internal structure to enhance its performance. Shifting boundaries, reshaping the crystal's internal landscape. As we apply an electric field and the crystal undergoes electrostriction, something remarkable happens at the boundaries between twin domains, the domain walls. These walls, which were once relatively immobile, begin to shift and reorient themselves. Imagine a line of people shuffling along as more people try to squeeze into a crowded space. Similarly, the domain walls move and adjust in response to the changing electric field and the resulting lattice strain. This movement isn't just a temporary rearrangement. The domain walls can become pinned in their new positions, resulting in a more stable and permanent change in the crystal's internal structure. It's like the difference between drawing a line in the sand and carving it into stone. This pinning of domain walls has significant implications for the long-term stability and performance of perovskite devices. Induced polarization, aligning dipoles for enhanced charge. Separation. Within each domain of our ferroelectric perovskite, we find tiny electric dipoles. These dipoles, formed by the separation of positive and negative charges within the material, are like tiny compasses, each with a north and south pole. When we apply an electric field, these dipoles experience a torque, causing them to align themselves with the field. This alignment of dipoles leads to a phenomenon called induced polarization. Imagine a field of sunflowers all turning to face the sun. Similarly, the dipoles within the crystal align themselves with the applied electric field, creating a net polarization within the material. This polarization plays a crucial role in enhancing the charge separation process, essential for the efficient operation of solar cells. A synergy in action lattice and photovoltaic fields join forces. Now, let's bring in the element that makes perovskites so special for solar energy: sunlight. When light strikes a perovskite solar cell, it creates pairs of excited charges, electrons and holes. These charges need to be separated and collected to generate electricity. This is where the synergy between lattice polarization and the photovoltaic electric field comes into play. The electric field generated within the solar cell by the absorbed sunlight works in tandem with the induced polarization of the perovskite lattice. Think of it like two teams working together to pull a heavy rope. The combined effort of the photovoltaic field and the lattice polarization enhances the separation and collection of charge carriers, leading to a more efficient conversion of sunlight into electricity. A brighter future enhanced solar cells through crystal engineering. The ability to manipulate the domain structure and polarization of perovskites through electric poling has profound implications for solar cell technology. By optimizing the alignment of domains and enhancing charge separation, we can significantly improve the efficiency and performance of perovskite solar cells. This newfound control over perovskite's internal structure opens up exciting possibilities for crystal engineering, designing and tailoring materials at the atomic level to achieve specific properties. It's like having a toolbox filled with atomic-sized tools, allowing us to sculpt and refine the material for optimal performance.